to do for this exam. Now, there's lots of individual skills that you need to be able to put together into one problem. Like, you may not have a standalone question that's converting between radians and degrees on the exam, but it is still a skill you might use on another problem, if that makes sense. So anyway, what do you remember? How do we get it out of radians? 180 over pi. Yep. So then we have pi cancels. 2 goes into 180 90 times. Then we have 90 times 11. 990 degrees. Questions? Radians to degrees. Okay. When would that be useful? I know it's not seeming to be useful on just a standalone problem, but can anybody think of a context where it would be useful to convert out of radians into degrees? What do you think?
To find like the angle, so we can find the coterminal. Maybe that's not the word for it, but like the reflected angle.
Sure.
Reference angle. That
Reference angle, yeah. We're going to have a couple of problems where I'm going to ask you to do like the sine of 5 pi over 7. So would you rather do sine of 5 pi over 7 or the sine of whatever the degree measure is? Probably degree measure, right? So, okay. Or for part B, it's helpful if you want to find coterminal angles. It might be easier for you to find coterminal angles when it's in degrees rather than in radians. So now that we have 990, that wants to find one positive and one negative coterminal angle. So coterminal just means going around the circle, either positive or negative, doesn't matter. They want a positive and a negative. So if we took 990 and subtracted 360, that's going to be one less revolution of a circle. That's one possible answer. I could very well have added 360 and gotten a coterminal angle, so there could be a whole bunch of different kind of answers for this one.
So if you, sorry.
Go ahead.
So if you like just minus 360 until you get into like the negatives, say the first one you come across is negative 90, that could be a coterminal angle?
Absolutely.
And then if you wanted, you could use like that one as the positive, even though you minused.
Mm-hmm.
Would you want to add, or would it matter?
Doesn't matter. Yeah, if you added 360, you'd get a positive. But since we have such a big angle, 990, if you subtract 360, even if you subtracted 360 twice, you'd still have a positive angle. And technically,
Right.
Those are all coterminal.
Okay.
So I got to keep subtracting 360. And let's see, 5, 13, 7, 270. So either one of these would work, honestly, for positive coterminal angles. Neither one's really better than the other. And then to get the negative, we're going to have to subtract one more time. So 270, subtract 360. Looks like we're going to have negative 90. So negative 90 would be one of your negative coterminal possibilities. If I didn't like 90 for some reason, what could I do to get another negative one? Just keep subtracting 360. Yep. So, questions on coterminal angles. Again, you may not have a standalone question that says find a coterminal angle, but when would this be a useful skill? What if I asked you to evaluate the sine of 630 degrees? What would be your first thing to do, the sine of 630 degrees? Find a reference angle, yes, I would, but before doing that, I would subtract 360 to find a coterminal, something between 0 and 3. So anyway, finding coterminal angle, pretty important thing. Yeah?
Say the degrees in radians, do you want the answer in radians, or are you fine?
I'm fine either way. Yeah. So the question was if the beginning problem starts in radians and it says find coterminal, technically your answer should be in radians also, but I really wouldn't care one way or the other.
It specifies in degrees though.
Does this one specify? Oh, sweet. Ooh, we got lucky. In degrees. Okay. Find the length of the arc and the area of the sector. Couple of formulas to remember here. Arc length, S equals radius times the angle, but you need to remember something particular about the angle. Angle has to be radians. So 60 degrees needs to be converted into radians out of degrees. So this time I'm going to put 180 degrees on the bottom because I'm trying to cancel degrees and go into radians. So pi over 180, the degree unit of measure cancels. 60 over 180 is 1 over 3, so this is pi over 3 radians. That's going to be our new theta or angle measure. So now we're golden with the arc length. It's nothing more than radius multiplied by measured angle in radians. So 16 pi thirds, and technically since we're measuring a distance, it should have a unit of measure. Feet. Very good, very good. So that's arc length. Area of a sector. Boy, there's a glare on there. Can you guys see with the glare? Okay. The light's in there. So we have a formula there for the area of a sector. 1/2 r squared theta. We already have theta, pi thirds. We already have radius 16. So this is really nothing more than filling in a formula. 1/2 16 squared times pi cubed. Now let's see, 16, 200 something, 200 and, is it 256? Okay. So 16 squared is 256. Half of that would be 128. So it would be 128 pi thirds. And this is an area, so it needs a unit of measure, but since it's an area, it's square feet. Yep. Okay. So what questions do we have regarding arc length or area of a sector? Yeah.
So, we'd have to use radians in the area of the sector formula too?
Yes, both of these you have to be in radians. Yep.
Okay.
Good question. Yeah.
What's pi? There was a formula in the book. It was like pi times the radius times theta.
Pi times the radius times theta.
I saw that as like the area or something. I'll have to pull it up.
Yeah, we did area of a sector in, when was it? 2.1, I think? That might be linear versus angular speed. I'm not sure. That one doesn't sound super familiar. Was it in our notes?
I'd have to go back to the notes and see.
Okay.
Something.
Yeah, if you run across it, bring it up when we talk about it. Yeah.
So in our notes, or at least what I wrote down, I couldn't actually decipher what the equation was, so I went online and looked, and there's a different equation. I don't know if it's true or false, or if it even
False.
works. It's false.
I don't know.
Alright.
I don't know.
No, but it was 1/2 times the beta r squared, and then they times it by 2 pi divided by 360.
Oh, so that's,
And then they pretty much just like rearranged it, so it was like the degree over 360 times pi r squared.
yeah. That's if the angle is given in degrees. So that formula includes converting degrees into radians automatically.
Okay.
Does that make sense?
Yeah.
Yeah.
So, but it's the same.
It's the same formula, it just converts degrees to radians for you inside the formula.
Cool.
So I guess it wasn't false. Math is still true. Whew! I started to doubt there for a second. Okay. Any other questions? These are all good questions. Fantastic.
Slide over.
Whoop. Slide it which way? This way? Or that way?
Yeah, that way.
There we go.
Thank you.
You're welcome. Now, we're getting into some important stuff. One of the main topics of this test is going to be evaluating trigonometric functions, and it's going to be evaluating several different ways. This is one type of evaluating on a right triangle. This is just one type. And then if you look at question 4, this is another type of evaluating a trigonometric. And then question 5 is another. So there's several, when I say evaluate a trigonometric function, there's several different instances of that. Question 3 being one of them. So we need all 6 of them, though. Sine, cosine, tangent. Let's start with those 3. Yeah, and we have a missing length here. So in relation to where theta is, that would be the adjacent length. But it's either A or B of a right triangle. So I'm just going to call it A. Because C always has to be the hypotenuse right here, so we can't call it C. So I'm just going to call it A. You can call it B, B or A. Now, Pythagorean Theorem would tell us that A squared plus B squared equals... It's out of what now? Oh, no. Come on now. Is it autofocus?
It does, but I think I couldn't.
There you go, there.
There it goes.
It's just focusing on your hand when you're writing.
Okay. There we go. Now, I do tend to see a few arithmetic mistakes with a term like this, in particular, 4 times square root of 5 squared. Yeah.
So you don't have to rationalize the denominator.
No. Mm-mm. So you just want to be careful with this. 4 times the square root of 5 squared. If you want to do it on a calculator, that's fine, or if you feel comfortable doing this by hand. Really what it means to square something is multiply it with itself. So if you have 4 square roots of 5 times 4 square roots of 5, it's 16 times the square root of 5 times the square root of 5, which is 16 times 5. Or this is the one case where you can distribute. This is the only time you can distribute an exponent if there's no plus or minus inside the parenthesis. So it's 4 squared times the square root of 5 squared. So 16 times 5, that would be what, 90?
80.
80? Close enough. 80. And then subtract 64. Oh, nice. And if you take a square root on both sides, we determine that A equals 4. But really, truly, I mean this sincerely, this is by no means meant to be done by hand. If you use a calculator, that's 100% okay to do 4 times the square root of 5 squared. Now, at this point, it's just up to you to remember what the definitions of sine, cosine, and tangent are as it relates to a right triangle. Sine was opposite over hypotenuse. Now, somebody asked, do we need to rationalize the denominator? What that means is, are we okay with square roots on the bottom of a fraction? I'm okay with that. So yes, you can leave the square root of 5 there, but technically the whole fraction is not simplified. 8 divided by 4 can simplify to 2. So you would be expected to at least simplify the fraction as far as you can go. Did that make sense?
Is that an 8 on top?
Say that again.
Wouldn't that be an adjacent number 8? Is an opposite?
No.
So the theta symbol is right here. Yeah, so opposite that theta symbol would be 8. Does that answer your question?
Yeah, that does.
Okay. I saw another hand raised. Yeah.
Well, I just wanted to make sure. So C squared is also hypotenuse.
C squared is hypotenuse. Yep. Okay, cosine. Cosine would be adjacent over hypotenuse. 4 divided by 4 is 1, so this would be 1 divided by the square root of 5. Tangent. Remind me about tangent. Tangent. Opposite over adjacent. Sweet. Now, cosecant. Now that you have sine, cosine, tangent, the other 3 should be relatively easy to figure out because they're just the reciprocals. Cosecant would be the reciprocal of sine. So square root of 5 over 2. Which one is the reciprocal of cosine? Secant. Yep, secant. Yeah, you're okay writing it as root 5. And if you write it as square root of 5 over 1, that's fine. I'm not going to mark it wrong. And then cotangent would be the reciprocal of tangent. Now, tangent is 2 over 1, so if you find the reciprocal of that, it would be 1/2. So again, if you look at the self-reflection here and say, all right, question 3, I'm not real sure about question 3. You can look, all right, on the self-assess, question 3 comes from section 2.2.1. Check what the homework you've done. If you've done the homework and it's still not quite, maybe do a few more problems from that same section, get a little bit more practice just to help hone that skill. All righty? Okay. How we doing so far? Am I going too quick? We all right? Okay. Now question 4, this starts going into section 2.3 now. 2.3 was a big one. There's a lot of topics in 2.3, a lot of topics. Now I want to make sure that we understand what this is telling us, that the angle, ooh, that's nice. The angle is between 180 degrees and 270 degrees. What is that telling us? Quadrant 3. Why would that be good information to know? Which one is positive or negative? So in quadrant 3, if we remember, quadrant 3 is tangent or cotangent. So already we're thinking, all right, if we're doing cosine, but it's in quadrant 3, should my answer be positive or negative? Negative. Answer should be negative because we're in quadrant 3 and we're doing cosine. So whatever answer you get, just make sure it's negative. Now, they're giving us some information here that the sine theta is negative 5/13. So what that's telling us is the opposite length to theta is 5 and the hypotenuse is 13. Or so we need to solve for the other side. And if you want to do this with a triangle, you can just draw some random triangle. I like how I was doing that. And if I wanted to put theta here, for example, you could put theta anywhere except for the right angle. You don't want to put it at the right angle, but if theta is here, according to the information given, the opposite length should be 5 and the hypotenuse should be 13. So then we're just left trying to find the adjacent length. Well, the ratio is negative, but the actual side lengths of a triangle are going to stay positive. It's just negative because we're also in the third quadrant and sine is negative in the third quadrant. That's why the ratio is negative. So Pythagorean Theorem, right? And rather than a question mark, let's make an actual mathematical symbol. Let's call it A again. I'm going to find A. So A squared. You like that one? A squared plus 5 squared equals 13 squared. So that's 169. And then 25. And yeah, if you subtract 25 from that, you get 144. So A squared equals 144. So the adjacent length there equals 12. And we're going to make it negative once we do the ratio, yep. So if the adjacent length now equals 12, and we want to do cosine, cosine is adjacent over hypotenuse, so we're going to say the adjacent length is 12 and the hypotenuse is 13, but because we're in quadrant 3, as we just talked about, we're going to make that ratio negative, so it's negative 12/13. So if we were to change this problem up a little bit, see that's the thing, I'm going to get on my soapbox again here. If you can solve every problem on the review, that's awesome. If you understand every problem on this practice test, that's great. Does that mean you're 100% ready for the exam itself? Maybe. Maybe not, though, because is the exam going to contain the exact same questions as on this? No, things are going to change a little bit. So when you're trying to self-assess your readiness, don't just think, well, can I solve all of these problems? Think about what the topic is, and if you understand the topic and not just the question. Does that make sense, what I'm saying? So I've heard a lot of students say, well, I did every problem on the review, I understood it, but I didn't do well in the exam. It's because the exam isn't the same as the problems on the review. They're similar, but you've got to think, what could be different about this problem? If things were to change, would I still be able to do it? For example, if I erase cosine and put tangent, what would change? It would be positive, right? Because we're in the third quadrant. Or if I said between 270 and 360, but I kept it as cosine. then we positive, because in the fourth quadrant, cosine is positive. So as you're trying to study, don't just say, well, I finished problem 5 on the test or on the practice test. I think I understand it. Think about what the topic is. And you don't have to guess. You know what the topic is, because on here on the reflection it says question 5 from 2.3.4. You can see what that learning target is. Go back to your homework, do a little bit more research, see if you really understand it. Okay? All right. Off the soapbox. What questions do we have on number 4? Or something like for anything related. Like I said, I'm not just going to cover this practice test. If you have homework questions or anything at all related to anything we're doing here, go ahead and ask. We'll go here and then we'll go over there.
So the way I kind of came to it is I drew the unit circle and then I drew the triangle within the unit circle and the quadrant. And that's what I just kept 5 because if you drew it in the unit circle, the triangle is going down in the quadrant 3.
Mm-hmm.
So if x is y, then that's why negative 5 will be going down.
Sure. Yeah.
So that's kind of how I came to that.
That'll work. Yep, that'll work. Cool. You had a question.
Yeah, I was actually just looking over the first page, and for the learning targets, there's a part about linear and angular speed.
Yeah.
I went through the review, the other one that you posted, and maybe I missed it, but I didn't see this one.
Those were at the end with the story problems.
Oh.
And we have one of those here at the end of here, too. It's like a wheel's turning 5 revolutions per second. How fast is it going? Those are those. We'll get to those. We have some of those to do. Okay, question 5. Find the exact value.
I need to find reference angle.
Often we would. Mm-hmm. If the angles turn out to be between 0 and 90, then we don't need reference angles. But if they're bigger than 90 degrees, then we would need reference angles. So these ones would be, yeah, they're all in radians, which honestly, if you're okay with radians, you can keep it in radians. You don't have to change it. But I'm assuming most of it at this point are still a little more comfortable with degrees. So this would be, when it says find exact values, then the way it was presented in class was with the special triangles, the 30, 60, 90, or the 45, 45, 90. Now, I wasn't able, I have to submit the exam to the testing center a couple days in advance, and so I wasn't able to modify it after Monday. So I couldn't include that picture that I had on the board over there on Monday. But let me show you how to just quickly generate. You remember that unit circle picture I showed you? So if you think about the first quadrant, over here on the right, the x value is 1 and the y value is 0. That's pretty self-explanatory because this is a unit circle, okay? The top, now the x value is 0 and the y value is 1. Okay with that? Now, we have 3 points here in the middle. This one is 30 degrees, this one is 45 degrees, this one is 60 degrees. Or if you want to try to remember radians, 30 degrees is pi over 6, 45 degrees is pi over 4, and 60 degrees is pi over 3. Okay? Now, a quick way to remember how to fill these in. You see where my pen is pointing here at the 0? X has a value of 0 here. If you want to continue to the right going clockwise, then your x value would be 1 over 2. These are all over 2. Let me do that a little bit smaller. It's 1 over 2, and then the square root of 2 over 2, and then the square root of 3 over 2. 1 over 2, square root of 2 over 2, and then the square root of 3 over 2. And the nice thing about this is it's the same pattern if you start here and go this way. So looking at where my pen is pointing, the first y value here is 0, so then the next y value would be 1 over 2, then the square root of 2 over 2, and then square root of 3 over 2. That's a quick way to generate the first quadrant of the unit circle. And if you have the first quadrant, then everything else is just reflected, but you've got to consider which y value or x value becomes negative inside the quadrant. Does that make sense? Now, you can use the special triangles still, or you can use the unit circle to answer the question when it says find the exact value. Special triangles still work. It may be a little quicker to use the unit circle, but it's up to you. For example, sine of pi thirds 60 degrees, that would be this one right here, at 60 degrees. What's the definition of sine, not on a triangle, but on a circle? Y over r, but since this is a unit circle, r is 1, so it's just a y value. So at 60 degrees, sine is the y value, which is square root 3 over 2. Okay, so that's how you would use the unit circle to answer these. If you wanted to use the special triangles, then you would still want to say, well, what is pi thirds? It's 60 degrees. So you want the 30, 60, 90 triangle. 60 degrees would be the larger of the two angles there. And the sides of it are 1, 2, square root 3. And definition of sine on a triangle is opposite over hypotenuse. So you get the same answer, square root of 3 over 2. Okay. Cosine of pi thirds, again, pi thirds is 60 degrees. So if you wanted to use unit circle, the definition of cosine is x over r, and since it's a unit circle, r is 1, so it's just the x value. So cosine of 60 degrees would be the x value here, which is 1/2, or if you wanted to use the special triangle, 60 degrees, the definition of cosine would be adjacent over hypotenuse. So 1/2. Now, pi fourths is 45 degrees. So if you wanted to use triangles, you wouldn't use the 30, 60, 90 because that doesn't contain 45 degrees. So you want the other special triangle, 45, 45, 90. And that one is 1, 1, square root of 2. And then tangent is opposite over adjacent.
Do we have these at our homework?
Yeah, they were from 2 point something, 2.3.3 maybe? Somewhere in 2.3. Or if you wanted to use unit circle, what was the definition of tangent on the unit circle? Y over x. And 45 degrees is this guy right here, and y and x are the same, so it's square root 2 over 2 divided by square root 2 over 2, which is 1. So, now performing these this is just arithmetic from here on out. Square root of 3 over 2 multiplied by 1 over 2 is square root of 3 over 4 minus 1, but 1 is 4 over 4. You're going to want to get common denominator. And then once you have a common denominator, it'd be square root of 3 minus 4
So you've got to put the
over 4.
minus 4 after.
Yeah, because we're subtracting by 1, and you can't, subtraction isn't commutative, you can't switch the order of subtraction.
If it was add, it wouldn't matter, right? You could put
If it was adding, you could switch the order, yeah. Yep. Whew, that one took some work. We okay?
Wait, sorry, I got lost. How'd you get 4 over 4?
So this came from multiplying these, and then we had to subtract 1, but since this had a denominator of 4, I wanted to change 1 to be a denominator of 4. So 1 is 1 over 1, which is the same as 4 over 4. So just so they have the same denominator. Good question. Okay, yeah.
Can we just circle this and that's our answer? Do you want this to be in like a decimal?
So
Exact, like number?
not that. This one right here. That would be your answer. Yep. Whew. How are we feeling so far about this? I'm telling you, how should I explain this? The amount of confidence you bring with you going into an exam has a lot to do with how well you do on an exam. It really does. If you go into an exam thinking, man, I'm going to do terrible, guess what's going to happen? You will do terrible. It just happens. Your subconscious takes over, your negative thoughts take over, and you're going to do terrible. If you go in there thinking, I'm going to do pretty good because I've studied, I've done the work, you may not know everything with 100% accuracy, and that's fine. You don't have to at this point, but be confident. Okay, be confident. Knowing that this is not the only chance to prove that you know this material. Okay, and that's, I know test anxiety happens. I know it's a real thing, and it's hard to deal with. Trust me, I know. Just know this is not your only chance to prove mastery of this material. I have to have a test date. That's just how things go. But if you haven't got everything up to this point, that's fine. Get your test back, figure out what you haven't learned, redo the problems, figure it out, and then you can do test corrections. Because the point is that you learn the material by the time I give the final exam. Okay, so just relax when you're going into the testing center. Don't be nervous. You guys got this. And be confident, okay? Okay, question 6 is also from 2.3. This goes into the definitions of sine and cosine and tangent that aren't on a triangle, they're on a circle. So the sine of an angle when it was on a circle, somebody said it already, it was y over r. Cosine is x over r. And tangent is y over x. Now, where are we getting all these x's and y's and r's? We could get it if on a circle, yeah, it's coming from a circle, but primarily this is our x value, and that's our y value. Now so that's a good question. On the unit circle, I don't know if you heard the question, but her question was, is the radius always 1? And that's on a unit circle. So this picture that I drew over here?
So is it the hypotenuse thing? I mean the Pythagorean?
Exactly. On this type of a question, it's understood that r isn't 1. It might be, but it's not always 1. So here's one way you could do this. You don't have to draw it out, but if you wanted to, you could. So -6 and then -2 would put the point right here. And the radius would be the segment that goes out to that point. Well, since we're talking about distances, the radius is going to be positive. So that triangle has one side length of 6 and another side length of 2. And I know it's negative because we're in the third quadrant, but I'm just talking about straight up distances. We're going 6 units and then 2 units. So positive distances at this point. How do we find that hypotenuse? Okay. So 6 squared plus 2 squared equals c squared. That's 36 plus 4, so we have 40 equals c squared. So c is square root of 40. And you are going to need to be able to simplify that down as far as you can. The square root of 40 is 4 times 10. I know it's a lot of other products, but specifically 4 times 10 because 4 is a perfect square, and the square root of 4 is 2. So it's 2 square roots of 10 is what it would be simplified. So that's our r value. Rather than calling it c, and now I'm going to call it r. So r equals 2 root 10. Now that we have that, we're ready to fill this in. The y value is -2, and r is 2 root 10. And -2 divided by 2 is -1, so this is -1 over root 10. Cosine is x over r. So -6 over 2 root 10. And -6 divided by 2 is -3, so it's -3 over root 10.
So we'd be docked points if we didn't reduce it.
Plus I'd drive to your house and just give you hell, so don't do it. Don't do it, don't even think about it. And then y divided by x, -2 divided by -6. Positive 1/3.
Relates to quadrant right?
Yeah, so I'm glad you noticed that. So what quadrant are we in with that point, -6, -2? Which of these three trigonometric functions should be positive if we're in quadrant 3? And look at that, tangent's positive. Nice. Okay, but we've got to do the other three. Cosecant, whoops. It's the reciprocal, so root 10 over -1, which I'm just going to call negative root 10. Secant, so negative root 10 over 3, good. And cotangent, 3. Okay. We're making pretty good time. Oh, sorry, I didn't ask. Let me go back. On a question like this, really not much is going to change other than the coordinate. So it may be something in the fourth quadrant, maybe something in the second quadrant, beginning place, but the way that you solve it is exactly the same. You're given x and y, so you got to find r using Pythagorean Theorem and just set up your 6 trigonometric functions. Questions?
Oh, actually,
Yeah.
so we did kind of compress the root 40 into 2.
Yep.
It's just been a while since I've done that.
Okay. So the way that happened is I changed 40 into 4 times 10. And 40 is also 8 times 5 or 1 times 40, but I chose specifically 4 times 10 because 4 has a square root. So then one of the properties of square roots, if you have a product, meaning you're multiplying two things, you can change that into separate square roots. Square root of 4 times the square root of 10. And then square root of 4 is 2, so that's where the 2 came from. All right, 7. So somebody mentioned earlier, I think it was you mentioned it, reference angles. This is where you were going to see reference angles. When it says find the exact value, when we have all sorts of weird angles here. So a couple ways you could think about doing this. The most common way would be to draw the angle, just so you have a visual. 300 degrees would land you so 300 degrees is positive, so going counterclockwise, it lands in the fourth quadrant. But the reference angle would be the difference between the angle and the x-axis in that quadrant. So if you can measure it clockwise, it's -60, but if you go the other way and go counterclockwise, it's 60. And we always want positive reference angles. So the reference angle I'm going to call 60 degrees. That's the reference angle there, 60 degrees. So rather than doing sine of 300, we're going to consider the sine of 60 degrees because the sine of an angle and the sine of the reference angle are the same value. It's just we got to consider whether it's positive or negative. And let's decide right now, if we're in the fourth quadrant and we're doing sine, it's negative because in the fourth quadrant, only cosine is positive. So whatever value we get from the sine of 60, we just got to turn that negative, and then we'll be good to go. So yeah, if you wanted to use your 30, 60, 90 triangle again, for 60 degrees it was 1, 2, square root of 3, and then since sine is opposite over hypotenuse, it would be square root of 3 over 2. So the sine of 60 is square root of 3 over 2, which means the sine of 300 is negative square root of 3 over 2. Now that's if you want to use a diagram with your special triangles, which is totally fine. It is a little more common to do it that way. If at some point in the exam you've drawn your unit circle somewhere, let me explain how this would look on a unit circle. So 300 degrees would be this point right here on the unit circle, which is a reflection of that point right there, right? That point at the top of the unit circle gets reflected to the bottom of the unit circle. So what changes if I reflect the point upside down? The y value is negative. So then it would have a location of 1/2 negative square root of 3 over 2. And then from there you just think, all right, we're doing sine. Sine is the y value. So at that point, the y value is negative square root of 3 over 2. So it gives you the same answer as using reference angles and special triangles. Yeah.
Well, just a question about like the reference angle. So,
Uh-huh.
so we got to 60, and is that just implying that 60 is the theta, and that's how we can like do the square root of 3 over 2?
Yeah. Yeah. Because 300 degrees and 60 degrees, the reference angle and sine of 300, they're going to have the same value. But one's positive, one's negative. Okay, 11 pi over 4. That's going to be a couple turns of the circle, I believe.
Is it 495?
So you're doing what I probably would do also. I'd get it out of radians into degrees. So multiply by 180 over pi. And 4 goes into 180 45 times. And then 11 times 45 is something. 495? Thank you. So rather than doing 11 pi over 4, we can consider tangent of... Now this is what I was talking about right at the beginning when we started this. I said you might not have a standalone question that requires you to convert between radians and degrees, but it's still a useful skill that we did here. So knowing how to convert out of radians into degrees is useful. And then even the second question we had, which I think was coterminal angles. You might not have a standalone question about coterminal angles, but now it's coming up here, tangent of 495. 495 is more than one revolution of a circle, so we've got to cut it back down by subtracting 360, which would be a coterminal angle. So rather than 495, we can cut that down to 135 by subtracting 360. And now we do reference angles. If you want to draw a diagram of that angle, 135 degrees would put it smack dab in the middle of quadrant 2 right here. That's 135 degrees. It's in quadrant 2, yep. So then the reference angle would be the difference between the terminal side and the x-axis. So if we're at 135 degrees and we need to go to 180 degrees, the difference is 45 degrees. So we have a 45 degree reference angle. So then you'd want to do the 45, 45, 90 triangle, which is 1, 1, root 2. And then tangent is opposite over hypotenuse. Or sorry, opposite over, bleh. Don't listen to me. Opposite over adjacent. But we're in quadrant 2. And in quadrant 2, tangent is negative. So we're going to call this negative 1 over 1. Or simply negative 1. Again, that's if you want to use a diagram of the angle with the reference angle. If you want to use the unit circle, 135 degrees is this point right here, which is a reflection of this point across the y-axis. So now the x value is negative and the y value is positive. So tangent, though, is still y over x, and they have the same value, except one's positive, one's negative. So if you divide one by the other, you get negative 1. Okay.
Sorry, what was the answer for B?
Negative 1. Where did we go wrong?
Let's see, so you got, can you zoom out for a sec, sorry. Tangent of 135, I got that. The reference angle is 45.
Mm-hmm.
And so I got my opposite, which is 1 over 1 over root of 2.
So that would be sine. That would be opposite of hypotenuse. You want tangent, which is opposite over adjacent.
Oh, gotcha.
1 over 1.
That's like,
And
Yeah.
the negative came from it being in quadrant.
It's in quadrant 2. And in quadrant 2, only the sine is positive. Tangent would be negative. All good questions. Alrighty, 2 pi over 3. I'm assuming we're going to want to take that out of radians.
No, just leave it.
Or just leave it in radians. There's no problem. We love everybody, right? We don't discriminate. So 3 into 180 is 60. And then 60 times negative 2 is negative 120. So really we're talking about the cosecant of negative 120 degrees. So you've got to be a little more mindful of, if you're going to draw a diagram of this, you've got to really think, all right, this is a negative angle. How do I graph a negative angle?
The opposite, right?
It's clockwise, yeah. So your initial side is still here, but the terminal side clockwise is going to go this way, 120 degrees. So it's going to end up right there. So this is negative 120 degrees.
Negative, would the reference angle still be 60?
Yeah, reference angles are always positive. That's a good question. So the reference angle is the distance between that terminal side and the x-axis, which is 60 degrees. So we have another 30, 60, 90. And if I put the 60-degree angle there, then I got 1, 2, square root of 3. And boy, now we got to remember cosecant. It's the opposite of sine, or reciprocal of sine. Sine's opposite over hypotenuse, so then you flip that upside down, and it's hypotenuse over opposite. Hypotenuse over opposite would be 2 over, but now we consider, hey, wait a minute, this is third quadrant. And in third quadrant, only the tangent is positive, so this has got to be negative 2 over root 3. Okay. So we're still doing okay on time. I had to speed things up here a little bit if we're going to get to those awesome story problems. Now, we've got the great opportunity to graph, which our most favorite thing in the world probably. So it's already at the top of its amplitude, and here's the midline, and then it ends at the top. So just that information tells us cosine. And because it's going up to 2 and down to negative 2, it's amplitude of 2. So I can already say that y equals 2 cosine. Now, yeah, the period starts at 0 and ends at 6 pi. So period is equal to 2 pi over b. That's the formula. The period equals 2 pi over b. And since I already know period, I've got to figure out what b equals. So if I solve this, I'm going to multiply it by b on both sides. Now I've got b times 6 pi equals 2 pi. Divide by 6 pi, so b equals 2 pi over 6 pi. There's 1/3. So maybe I should have started with this. The form of the equation that you're going to look for is y equals a cosine bx, or it may also be a sine bx. What would have to change in order for this to be a sine graph? Starts at the midline, 0. Yeah. So I knew it was going to be a cosine because it started at the top of the amplitude. And so that's why we had to find the value of b, which was 1/3. So you could write this as 1/3 times x. That's fine if you want to write it that way. Or you could write it as x over 3. Same thing. Questions? The period, since it started here at the top and went through one full cycle and ended here, then the period was right there, 6 pi, 0 to 6 pi. So the period was 6 pi.
How did you find B?
The formula is period,
Oh, we can see.
period equals 2 pi over b. That's the formula from section 2.5. So I just replaced the word period with 6 pi because that's what the period was 6 pi. All right. Tangent. Now, it hasn't been a lot of time since we practiced. I think it was just Monday, was it, where we talked about tangents? So you might not have had a lot of practice. Keep doing the homework. Keep trying some of the review problems. Do some of these. But you are going to have a familiarity with graphing sine, cosine, tangent, cosecant, all of those. You need to be familiar with graphing all 6 of them. Okay. Tangent, cotangent were much, much different than sine and cosine. Sine and cosine are what are called continuous functions. You just start at one end, you go to the other end without interruption. There's no vertical asymptotes. Tangent has vertical asymptotes. Typically, so let me just go into some background. Typically, if you want the parent function of tangent, there were vertical asymptotes on either side of the y-axis, and one of them was negative pi over 2, the other one was pi over 2, which gave us a period. What's the total distance from negative pi over 2 to pi over 2? That gave us a period of pi. That's the parent function, but we've got some transformations here. We've got this change in it, we've got that change in it, so that may increase or decrease the distance between our vertical asymptotes, right? So we need to find the period first. Period of sine and cosine, let's review this right now. Period of sine and cosine? 2 pi over b, that's how we find the period, 2 pi over b. Period of tangent, cotangent is pi over b. So the period here is going to be pi over b. That has a coefficient of 1 over 2. So pi divided by 1/2 is 2 pi. So the total distance between both vertical asymptotes has to be 2 pi. So I'm going to still put one here and put one right here, but rather than calling one of them negative pi over 2 and the other one positive pi over 2, if I want a full distance of 2 pi, I should call that one negative pi and positive pi. Okay. Now, the shape of the tangent graph, it comes through the middle. Wherever you have your two vertical asymptotes, the tangent is going to come through the middle of that and have this kind of a shape. Now, I just for the sake of time, I didn't really have time to cover what effect this number actually has. We would all agree that that changes the graph in some form, right? That 2 there. Since it's, wait, come on, focus. Well, anyway, since it's outside the function, it's a vertical compression or a stretch. And since it's bigger than 1, it's a stretch. So it actually stretches the graph out a little bit vertically. For those that want to be more precise, and I'm not going to dock you one way or the other, but for those that want to say, well, I'm going to be a little more precise, the way that this is done is once you have the location of your two vertical asymptotes, you could split that distance in half. And again, I'm not saying this is the way it needs to be done on the test. I just wanted to be a little more thorough for those that want it to be. What's the location at this point right here? Pi halves. So here's what you would do. Now you go and say, well, if my x value is pi halves, I would have 2 times the tangent of pi halves over 2. That's a crappy looking 2. What is pi halves over 2? Pi over 4. So then this becomes 2 tangent of pi over 4. And pi over 4 is 45 degrees. What's the tangent of 45 degrees? 1. So then this turns into 2 times 1, which is 2. So when I plugged in pi halves for x, what did I get for y? 2. So then that gives me one more point here, and then I could reflect that down here. So that just gives me a little bit better idea of the actual shape of the graph. So that's a little more precise way to do it. But expectations for you, since we didn't really have time to cover that, for tangent and cotangent, you need to have the correct spacing between your two vertical asymptotes, okay, and the correct shape of the graph. Now, what if this were cotangent?
Start at the top.
The asymptotes don't split the y-axis. On cotangent, one of the vertical asymptotes is on the y-axis, and then whatever the distance of your period, then you would place the other one. So for example, if the only thing that was different on this is that it was cotangent, how would that change this picture? It's the vertical asymptote would start on the y-axis, which is 0, and it still had the same period, 2 pi. So if my first asymptote is at 0, where would I place the other one so that I have a period of 2 pi?
2 pi.
At 2 pi. So to have an asymptote at 0 and then one at 2 pi.
Okay, so cotangent always has an asymptote.
Yeah. And then the shape of the cotangent is a little bit different than the shape of the tangent. Remember that? Cotangent has that kind of a shape, right? Anywho.
Looking at it, if it was a cotangent with this particular one, it would shift over.
Right.
Yeah. So, whoops. There it is. If this were cotangent, let me just sketch it real quick. You'd have a vertical asymptote at 0, and then since the period is 2 pi, you'd have another one over here, and you'd call it 2 pi, like that. And then somewhere in the middle, it's going to cross through the middle, and then the shape would just look like that, and that would be your cotangent.
Cross that pi.
Yeah. All right. There we go. Woo! Okay, we have 15 minutes. Let's do this. Cosecant 2x. Y equals 3 cosecant of 2x.
Should we jump to the first problem? First graph is if it's sine, right?
This would be a good one to cover, though. We would graph it first as if it were sine, because cosecant and sine are very much related. So I'm going to forget about cosecant for a second and focus on sine. The sine function starts at the midline, which is 0 in this case. And then we would want to consider an amplitude here, 3, and we would also want to consider a period, which would be 2 pi over b, which is 2 pi over 2, which is pi. So then you go out some length, doesn't matter exactly how far, and call that pi. Now I want to make sure you're listening carefully. If you are graphing sine, cosine, cosecant, or secant, those four, and the graph hasn't moved left or right or up or down, you do need to label your x-axis according to however you split it up. So if I'm going from 0 to pi, you got to split that into quarters. So halfway would be pi halves. Halfway between that halfway would be pi fourths. And then this one here would be 3 pi fourths. So you need to correctly split that up. And then draw your sine graph, but I'm going to do it with a dotted line since this is not really a sine function, it's really a cosecant function. And yeah, first do the asymptotes. Any place this sine graph crosses the x-axis, you would place a vertical asymptote. So at pi halves, and right on the y-axis. And then you invert up here. And down there. So if this were secant, for example, secant, if this were secant, only difference, you would graph cosine first, which would start at the top. So the graph would look a little different because you're graphing a cosine. All right? Okay. For the sake of time, okay, question 11 is from section 2.7, graphing a trigonometric function that involves vertical and horizontal translation. And the horizontal translation is referred to as a phase shift. So for part A, amplitude would be the value of A there. Period would be using that B value. So amplitude 2 period, since we're talking about the sine function, would be 2 pi divided by B in that case, which is 2. And the phase shift can be found using the formula opposite of C over B, where this is C and that's B. The opposite of C would be positive pi halves divided by 2, which is pi fourths. What this means is there's a shift to the right, pi fourths of a unit. So we shift right pi fourths, and then we shift down 3 units there. So the idea for graphing these types of graphs with horizontal and vertical translations is you actually shift the whole axis system and you create a new set of axes centered around the point. In this case, I'm going to shift, so let's be pi fourths, pi halves, 3 pi fourths, pi. So if I go to the right, pi fourths of a unit, and then down 3 units, that would give me a point right here. So what I'm going to do is create a new set of axes. Where the origin of this new set of axes is centered at that point, pi fourths, comma -3, and now I'm just going to graph a sine function with the same amplitude and same period, just without the transformations of moving to the right and moving down. So in this new set of axes, the period is still pi, but since I'm starting at pi fourths, I have to go out a distance of pi from pi fourths, so that's going to actually come all the way to here to 5 pi fourths. Because if I start at pi, or rather pi fourths, and add a full period, which is pi fourths plus pi is 5 pi fourths. And if you remember, the sine function starts at the midline, so it's going to start there. It's going to come up to the top of its amplitude, back down to the midline, and then come to the bottom of its amplitude, and then back up to the midline. Yeah, so this one's nearly identical. The one formula you're going to want to remember that relates linear speed to angular speed. And before I get into this, I just want to clarify. Linear speed. What is meant by linear speed? Something related to distance over time. We could think about it that way. Yep. If I'm driving a car 60 miles an hour, that's linear speed, right? But it's not just if you're driving in a straight line or making forward progress that denotes linear speed. If I'm somehow at the end of some kind of a circle and I'm spinning around and I calculate my speed is going at 40 miles per hour, even though I'm going in a circle, but my speed is 40 miles per hour, what's that an example of? That's still linear speed, okay? Angular speed is how many revolutions or how many radians I'm turning per unit of time. So if I say, well, I'm turning 40 miles per hour, but I'm going 3 revolutions per minute or 4 pi radians. That's all example of an angular type speed. Do you understand the difference there? So this, for example, 5 revolutions per second. That means it's calculating how many revolutions it's doing per unit of time. So that would be a form of angular speed. We need to calculate that into radians to be really, truly angular speed. But they're asking for the linear speed in miles per hour of the tips of the blade. So the tips of the blade are still moving in a circular motion, right? But if I could clock their speed in miles per hour, that's an example of linear speed, even though they're going in a circle. So just don't want you to get confused there. So the formula is linear speed v is radius times omega, where omega is the angular speed in radians per unit of time. Let's take an inventory. What they're asking us to find is v, so obviously we don't know v because that's what we're supposed to find. R stands for radius. Do we have any kind of radius in the problem?
Yes.
15 feet. So we have radius. We're good on that one. Now, omega stands for angular speed in radians per unit of time. So do we have angular speed in radians?
No, we don't.
No, we have it in terms of revolutions. So this is kind of like what omega needs to be, but it's not in radians and revolutions. So I'm first going to deal with that 5 revolutions per second. So 5 revolutions per second needs to go through a couple of conversion factors. If it makes 1 revolution, that's 2 pi radians. So there's our conversion factor. 1 revolution is 2 pi radians. Now, where do I want? So 2 pi and 1 revolution is the same thing, but where am I going to put the 1 revolution, top or bottom? Bottom, because I want it to cancel this revolution. I want to go out of revolution, so I want to put 1 revolution on the bottom of this and 2 pi radians at the top of it. So now this is 10 pi radians per second. That's my omega, 10 pi radians per second. Now, we can either convert it now or we can wait till the very end of the problem, but the linear speed needs to be in terms of hour, and now we have seconds. So at some point, we're going to have to convert this into hours. Might as well do it now. So let's convert 10 pi radians per second into radians per hour.
Wait, what? 60?
So we could do it either if you happen to know how many seconds are in an hour, you can just go straight to it. But if you want to go from seconds to minutes and then minutes to hours, then 60 seconds is 1 minute. And then you can use another conversion factor and say 60 minutes is 1 hour. This dimensional analysis is really useful in all sorts of fields, physics, chemistry, math. So it's 3,600 times 10, which would, be 36,000. 36,000 pi radians per hour. No, that's the omega. So now the formula says, what do we do with omega? Multiply it by r. So now I take 36,000 pi radians per hour and multiply it by 15 what? 15, that's a problem. You know, like your feet should be in miles per hour, dang it.
There's an extra 0 on there, I think. 60 times 60?
But then remember we multiplied that by 10 there to get the 36,000. Yeah. All right, so feet into miles. I want the feet on the bottom and miles on top. And this is just one of these things that I know it's not maybe common knowledge, but it is useful to try to remember. 1 mile is 5,280 feet. So 1 mile is 5,280 feet. So now I cancel the feet unit of measure. And it's best if you leave this answer in terms of pi, meaning leave pi in your answer. Don't multiply it into the number and give me a decimal. Just give me an answer in terms of pi. So what you would need to do on a calculator is 36,000 times 15. Divide all that by 5,280. I'd recommend using a calculator. You don't have enough fingers and toes to do that without a calculator. And if it doesn't divide evenly, then dang it, we have to do a simplified fraction.
What?
Does it
225 over 20.
225 over what? 22 pi. You know what? This would be so much easier. This would be so much easier if you just did it with a decimal. Just multiply pi in there. I'm okay with that. So 36,000 times pi times 15 divided by 5280. 10.2?
Yeah, 22.
10.22. Now, if you're having trouble finding pi on your calculator, you got 102? I'm trusting you guys here on this one.
Oh, sorry.
So 102.
3,600 pi, or 36,000 pi times 15. That's where we're at right now, right?
And then you divide it by 5,280.
Okay.
And then, if your calculator doesn't have a nice, easy pi button, then just multiply it by 3.14. It's going to be close enough.
21.
You got 321.
What?
Yeah, we didn't have pi in our 102, so that's probably right.
Oh, did you multiply that by pi?
Not in your 102, so yeah, that's right.
I didn't get any of those answers.
102 times 50.
Well, maybe math isn't true anymore.
So 36,000 pi times 15 divided by 5280.
Yes.
321.
I got 321.9.
All right.
That's what I got.
Oh, it's because you put the pi.
Math is true.
Yeah, that's what they got.
321.3
I was hearing like 10.
miles per hour.
Wow, that was so fun and awesome.
Can you imagine if you were on the end of that thing, you'd be going 322 miles an hour? That would be awesome.
Wow, okay.
No, I don't want to move on till we're okay with this. It was a lot of dimensional analysis, but in the end, really all it came down to was multiplying a bunch of stuff together. 36,000 times pi times 15 divided by 5,280 equals 321.3.
Is it okay if we just write pi? Or do you want us to add it?
It actually makes more sense in an application problem to multiply pi in there, because if somebody's trying to calculate a speed, they're not going to say, well, that's 102 pi miles per hour. I mean, that's kind of a cumbersome way of, you know what I mean? So it probably would be better just to multiply it in there and get a decimal. Okay, we got to hurry and finish this last one. Number 13. So hopefully this guy's far enough away that he can get burned by the rocket when it went off.
1.4 miles.
That's probably far enough. Now, after 5 seconds, he has this little gizmo here that helps him calculate that the angle of elevation there is 42 degrees. At that exact moment, that rocket is 42 degrees angle of elevation. So if we were able to spend time and the rocket froze there at 42 degrees, how high is it? And then what's the distance from the observer to that rocket at that moment of time? So we have this measurement given to us. We're trying to find, let's do one at a time. Let's find h first.
Do we do the sine or no? Cosine of 42 is 1.4.
Okay, you're getting close. Now, I see why you're choosing cosine, because we have adjacent, but cosine deals with adjacent and hypotenuse, so that would help us find d.
Tangent.
So if I want to find h specifically, h is the opposite length of 42 degrees, and that's the adjacent. So opposite and adjacent would be better to use tangent. Opposite and adjacent would be better to use tangent. So to find h, I would say that tangent of 42 degrees is equal to the opposite length, which I don't know, so I'm going to call h. divided by the adjacent length, 1.4 miles. Now hold on, I'm gonna hit the pause button. What are we solving for here?
H.
We're solving for H. We're solving for H. H is being divided by 1.4, so the opposite of that would be multiplying by 1.4. So H equals tan 42 degrees multiplied by 1.4. Now, one of the most common mistakes is user error on calculator. Calculators have two modes, radians and degrees. And the default on most calculators is actually radians. So if you type in tan 42 multiplied by 140 or 1.4, there's no guarantee that's the right answer. You've got to be 100% sure your calculator is in degree mode.
Especially if it's negative.
Yeah. So most calculator screens, somewhere on there either has a D or an R. That's what that, if you ever wonder what that meant, D stands for degrees, R stands for radians. So your calculator should be D for degrees. Now, what is tan 42 multiplied by 1.4? 1.26. And since this is an actual measurement, we need a unit of measure. Miles. Awesome. So that's H, right. Now, how do we find D? At this point, we have a couple of options. Yeah, you're right. We could do, so let me erase this. Now that we know two sides of a right triangle, this was 1.2. We could just do Pythagorean Theorem, a squared plus b squared equals c squared. That's fine. That's totally fine. If you wanted to continue using trigonometry, you could say, well, if I've got this adjacent length still, but I want the hypotenuse, which trig function deals with adjacent and hypotenuse? So you could do cosine. So it's up to you. There's two ways to do this one. Which one would you want to see in the next 2 minutes? We got to get out of here. The other class is going to start. Cosine? Okay, so cosine of 42 degrees is the adjacent length, 1.4, divided by the hypotenuse, which we don't know, D. So you're going to have to manipulate this equation a little bit. I'm going to go ahead and multiply it by D to clear the fraction. But now I've got D times cosine of 42 equals 1.4. So now you divide by cosine 42. So then D equals 1.4 divided by cosine 42. And you're getting 0.88? 1.88?
Yeah.
Now, let's just contemplate here for a second, because I'm always surprised at answers that students give that if you took a moment to reflect would be obviously wrong. This is a right triangle, yes?
Yeah.
Of the sides of a right triangle, which one should be the longest? So does that still hold true on what we've drawn here? This is the longest length. So just always things to consider when you're doing browsing. You know, does it make sense in the context of the real world? 1.88 miles, my apology. Miles. Whew, that could have been